Hello everyone, my name is Rakshitha. I'm pursuing my final year degree from Sri Venkateswara College of Engineering from the Department of Electronics and Communication Engineering. Today in this video, I'll be discussing my subject called Automotive Electronics. In this subject, I'll be discussing about CAN, LIN and most bus protocol and message frame format. So without any further delay, let's get into our video now. In this slide, we'll be discussing about CAN bus protocol and message format. So now let's see what is CAN bus. The CAN bus system enables each ECU to communicate with all other ECUs without complex dedicated wiring. Specifically, an ECU can prepare and broadcast information via the CAN bus. The broadcasted data is accepted by all of the ECUs on the CAN bus network, and each ECU can then check the data and decide whether to receive or ignore it. This is the general structure of the CAN bus protocol, and here we have the gateway. Gateway converts the nodes into the general data format. Here we have two diagnostic CAN, and this is the dashboard. Here we have OBD2, and here we have a driver CAN, comfort CAN, and infotainment CAN. We have engine ECU, transmission ECU. ECU stands for electronic control unit. We have ESP and ASCC. Here we have sensor CAN, and yeah, many etc. And this is the 7 layers of ISO model. This diagram tells us how ISO model is linked with the CAN bus protocol. In CAN we have 5 sublayers. First one is logic link control, media access control, physical coding, physical media attachment, physical media dependent. Here this logical, media and physical coding are related to data link. Media attachment and media dependent are linked to physical layer of the ISO model. In this slide, we'll be seeing what is CAN frame. Communication over the CAN bus is done via CAN frames. Below is the standard CAN frame with 11-bit identifiers, that is CAN 2.0A, which is the type used in most cars. The extended 29-bit identifier frame, that is CAN 2.0B, is identical except the longer ID for heavy-duty vehicles. Here first we have start of frame. Here we have ID, that is standard identifier. Here we have RTR control, that is remote transmission request. Here we have the data. Here we have CRC, that is cyclic redundancy check. Here we have ACK, that is acknowledgement. At the last we have EOF, that is end of frame. So now let's see what does each block do. Here first SOF, that is the start of frame. The start of frame is a dominant 0 to tell that other nodes that the CAN node intend to talk. Next ID. The ID is the frame identifier. Lower values have a higher priority. Next is RTR, that is the remote transmission request, indicates whether a node sends data or requests dedicated data from another node. The next one is the control. The control contains the identifier extension bit, which is the dominant 0 for 11-bit. It also contains the 4-bit data length code, that is DLC, that specifies the length of the data bytes to be transmitted from 0 to 8 bytes. The next one is the data. The data contains the data bytes payload, which includes CAN signal that can be extracted and other information can be sent. The next one is the CRC, cyclic redundancy check, is used to ensure data integrity. The next one is the ACK, acknowledgement. Slot indicates if the node has acknowledged or received the data. Next one is the EOF, that is the end of frame of the CAN bus. In this slide, we'll be discussing about LIN bus protocol and message format. So now let's see what is LIN bus. LIN bus offers low performance and reliability, but also drastically lowers cost. Below, we provide a quick overview of LIN bus and comparison of LIN bus versus CAN bus. Low cost option, often used in vehicles for window wipers, air conditions, etc. LIN cluster consists of one master and up to 16 slave nodes. Single wire with 1 to 20 kilobytes per second at maximum 40-meter bus length. Time-trigger scheduling with guarantee latency time. Variable data length, that is 248 bytes. LIN supports error detection, checksum, and configuration. This is the general structure of the LIN bus mode. Here LIN bus is going to the header and the response. Here we'll be having all the slave nodes. In here the LIN bus master node. And this is the diagram of how LIN bus is connected to ISM model. In this slide we'll be discussing what is LIN bus frame format. This is the structure of the LIN bus frame format. Here first we have LIN bus frame. It consists of break 14 plus bits. Here we have synchronization, that is of 8 bits. Here we have ID, that is the identifier, of 6 bits, and this is the header. Then we have the response. In response we have 16 to 64 bits of data and checksum of 8 bits. So now let's see what is the function of each block. First is the break. The synchronization break field, SBF, break is minimum 13 plus 1 bits long. The break field acts as a start of the frame. Notice to all LIN nodes of the bus. The next is the synchronization. The 8-bit synchronization field has a predefined value of 0x55. This structure allows the LIN nodes to determine the time between rising falling edge and thus the rate used by the master node. This lets each of them stay in synchronization. The next is the identifier. The identifier is 6 bits followed by 2 party bits. The ID acts as an identifier for each LIN message and sent and which nodes react to the header. Slave determines the validity of the ID field. Next is the data. When a LIN slave is polled by the master, it can respond by transmitting 2, 4 or 8 bits of data. Next is the checksum. As in CAN, a checksum field ensures the validity of the LIN frame. The classic 8-bit checksum transfers the data bytes only. In this slide, we'll be discussing about most bus protocol and message format. This is the general structure of the most bus. It performs various operations like audio, data service, graphics, video, and controlling. So now let's see what is most bus protocol. In automotive, most bus is a high-speed multimedia network that enables seamless communication between various components within a vehicle. It serves as a backbone for transmitting audio, video, and control signals, facilitating the integration of infotainment, driver assistance, and other vehicle systems. The most bus was designed to carry high bandwidth multimedia data over the vehicle. It was initially specified in the 1990s through joint effort from BMW and OASIS Silicon. Over the time, the consumption expanded to include more members, and today many OEMs use the automotive most bus to carry the multimedia data. In this slide, we'll be discussing about most most bus frame format. The most bus uses a specific frame format for transmitting data and control signals between network nodes. Understanding this frame format is essential for analyzing and interpreting the data exchanged on the bus. The frame format of the MOS 25 protocol consists of 1 byte header, 4 bits used for synchronization processes. The remaining bits in the header indicate the number of quadlets available for streaming data in the packet. Control data and frame control information follow the header, with the size of each control message being 32 bytes. The MOS 50 and MOS 150 protocols have different frame formats, but they share similarities with the MOS 25 format. This diagram shows the link between the ISO model and the MOST bus. In the MOST bus, we have functional block, network services, NIC, INIC, stream service, optical physical, and electrical physical. So thank you all for watching my video. Please do like the video, share and subscribe to my channel. Thank you all.